Green's theorem gives a relationship between a line integral around a simple closed curve and a double integral over the plane region D that's bounded by C. So what this is saying is, let's take a look at something here on the xy plane. And I have this curve, and I'm going to have my orientation. Now it's a simple closed curve on C, and inside here I have this region D. Now what Green's theorem does is it makes a connection between this curve and this region D inside, or that's in which the curve bounds. Now let's take just a moment to talk about orientation. The way I drew this with the orientation going counterclockwise, notice the region is always to the left. If I'm traveling in this direction, the region is always to the left in reference to where I'm traveling, counterclockwise. We refer to this as being positive orientation. If, on the other hand, I were going clockwise, going in the opposite direction, so the interior would actually be to my right as I'm traveling around the curve, this would then be referred to as a negative orientation. It's kind of important because I'm about to give you Green's theorem, and Green's theorem makes reference to a positively oriented, simple closed curve. The actual theorem says, let C be a positively oriented, piecewise smooth, simple closed curve in the plane, and let D be the region bounded by C. Now, if P and Q both have continuous partial derivatives on an open region that contains D, then the line integral of C, px plus, p dx plus q dy is actually equal to the double integral over D of the partial of q with respect to x minus the partial of p with respect to y dA. So saying I can actually find the value of this line integral by doing this double integral, which at times a function defining a line integral can be horribly difficult to work with, and this double integral can simplify things tremendously. Now there is some additional notation, some additional and alternate notation that's very commonly used to describe this scenario. Very commonly we see the notation of the line integral with a circle through it. So we may see it like this. And what this circle means, the circle indicates that we're integrating over a closed curve. And sometimes you also see this written not only with a circle through it, but a circle with an arrow, or perhaps the arrow may be on this side, that simply indicates the positive orientation. And yet another notation that is sometimes used to also indicate that positive notation is the notation that we use for a partial derivative. So very commonly you may see this written as the integral sign with this partial of D, where D is being the region. So just to sum up some of this notation, this notation is equivalent to this notation. Oops. which is also actually equal to the double integral over the region D of the partial of Q with respect to X minus the partial of P with respect to Y in reference to the area.